Okay, so for the last bit of knowledge from this class, what I'm going to talk about today is how Dantzig-Wolfe decomposition, what we basically covered in the last class, applies to two-stage stochastic programs, and what we will arrive to is the L-shaped algorithm from a completely different direction. And if we have any time left, we'll also discuss how you can use the algorithm for tackling integer programs. Again, the idea of the class is you learn, you get a toolbox and you can apply it to stochastic programming, which is the context of the class, but you can go beyond that and apply it to general optimization problems. This is a couple of slides that I mentioned also in the last class. When you see an LP that looks like this, you're in good shape for the L-shaped method, also known as, applying the L-shaped method to Bender's decomposition. So you ignore a bunch of these constraints, and you solve a small master, and then you add these constraints indirectly through optimality cuts. On the other hand, when you have an L-shaped, when you have a linear program that looks like this, you're in good shape for Dantzig-Wolfe. So large number of primal decision variables. What is going to look like this LP in our case today is going to be the dual of the two-stage stochastic program. So if you notice here, this is exactly the coefficient matrix of a two-stage stochastic program. AX equals B are the first stage constraints, and all of these constraints are second stage coupling with first stage decisions. If we take the dual of that problem, our constraint matrix looks exactly like this, basically. Okay, so in more specific terms, what I'm writing out here is the primal form of the two-stage stochastic program. The notation should be familiar. So I'm using rho to denote the dual multipliers of the first stage equality constraints, and pi k to denote the dual multipliers of the second stage equality constraints. If we take the dual of that problem, we arrive to something like this, which has exactly the form that I mentioned earlier. So this is indicator that you can be applying Dantzig-Wolfe. Why? Because we have a myriad, a very large number of decision variables, but we know that in any optimal basis, only m of them will be non-zero. So we might as well ignore the trillions of other ones that are following behind. And this is basically, okay, so when we're tempted to apply Dantzig-Wolfe, the first thing we want to ask ourselves is which polyhedron am I going to represent with Minkowski's representation theorem. It all starts from there. You pick a polyhedron to represent using Minkowski, and then you start bringing in the extreme points or the extreme rays of this polyhedron. So the way we're going to apply Dantzig-Wolfe in this specific problem, and admittedly there's a simpler way to write all of this stuff, but I wanted to be consistent with the notation in the book. So here's the polyhedron that we will approximate using Minkowski. And the notation that I will be using is pi superscript j are the extreme points of this polyhedron, and capital J is the set of extreme points. W superscript r are the extreme rays, and capital R is the set of extreme rays. I think from what Matthew told me, you kind of covered this stuff extensively last week, so no reason to remind what extreme points or extreme rays are. Okay. And what I'm going to introduce as a notation here is the following. This capital E subscript J matrix is extreme point J transpose inner product with these weighted T matrices little e vector is that same extreme point inner product with the weighted h vectors, and correspondingly for capital D and little d, instead of the extreme point, we have the extreme rays. Okay, if we apply Minkowski's representation theorem to this polyhedron and start thinking and think of our problem in terms of averages of pi variables and non-negative combinations of w variables, what we get is a problem like this. And the question I have, so this is really the just the original problem we want to solve. Nothing has really changed. What are we up? What's our decision variable? Lambda mu and rho. Exactly. And again, I want to emphasize, we've applied Dantzig-Wolfe not to the primary, to the dual. Rho is now a decision variable the same way x was a decision variable in last week's lecture. And we bring in the lambda and the mu decision variables. Okay, another question. And actually, this is the full problem, right? We haven't done any decomposition yet. We're considering the full population, which could be enormous. It will be, in general, enormous, of lambda variables and mu, so extreme points and extreme rays. These could be exponential in the size of the problem. Question for you is, what does the dual of this problem look like? What does the objective function look like? And constraints. So let's do with respect to lambda j. Again, to get the dual, well, let's do with respect to rho. Rho is a free variable. Shows up here and here. So here we take the dual x transpose A, or AX, and since it's a free variable, we have an equality constraint, and the corresponding coefficients of rho and the objective function are given. And with respect to the extreme points, the lambdas, what we have is lambda shows up here, and it shows up here and here. And it's also greater than or equal, so from the duality of linear programming rules, what we have is something that's going to look like this. So theta plus ej x plus little ej. Okay, and then for the mu variables, what we get is basically brx plus little br using the same rationale. Does this look like a familiar problem? This is exactly the L-shaped. In fact, it's the L-shaped we would have gotten if we were not at all economical. If we had all the optimality cuts and all the feasibility cuts that we could get, we would get a problem like this. Okay. So we're already starting to see that these two approaches are very closely linked. Now, in the Dantzig-Wolfe algorithm, what we would do is we would solve the master problem. We would get a bunch of lambdas and mu's, and we would then ask ourselves, okay, are there any non-basic variables that I need to bring in? And the trick, again, if you remember with the Dantzig-Wolfe, was that instead of going and enumerating one by one all the extreme points and all the extreme rays of this problem, we exploit the linearity of the reduced cost expression with respect to the dual to the variables. So if we use these formulas here, and I know it seems like I might be jumping a couple of steps, but the logic is exactly the same as what we saw last week. Basically, the sub-problems we would want to be solving is, instead of going and enumerating one by one all the lambdas and all the mu's, we can basically solve this maximization problem over here, which is an immediate shortcut. To get out of all the enumeration, we recast that procedure as a linear program. Why? Because the reduced cost of the non-basic variables can be expressed as linear functions of pi. And why is that true? Because of equations 1 and 2. So again, the philosophy in Dantzig-Wolfe is we're not going to enumerate all the non-basic variables one by one. We're going to solve an LP instead, because it so happens that the reduced costs are functions of our variables. Okay, so this is when we're applying Dantzig-Wolfe to the polyhedron I mentioned earlier. This is the sub-problem we get, subject to the sub-problem constraints. So these constraints are the ones who we did not that we did not approximate with Minkowski. So those come into the sub-problem. And if you take the dual of this problem here, what you get in the objective function is minimize Q transpose YK, subject to these constraints here. These should also look familiar. This is the sub-problem of Dantzig-Wolfe, and this is its dual, which is identical to the second stage sub-problem of the L-shaped method. So if we were going to apply the Dantzig-Wolfe algorithm to this problem, we would take the original master problem here, and the trick would be not to consider all the extreme points and extreme rays, but just a small subset, which I'm going to denote J tilde and R tilde. So that's what you just saw is exactly this LP here. It's just that instead of the full set capital J and capital R, we have subsets with tildes. And now what we've done is we've basically ignored a bunch of lambda and mu variables, and we're looking at a very small number of candidates. And these are the sub-problems of the decomposition, and this is kind of basically what the book gives you is this slide here. But that presumes you've kind of gone through the whole thought process that we've been going through for the last 1.5 lectures. So that's kind of why I wanted to spend a bit more time. Instead of just giving you the algorithm in the book, I wanted to make sure we would cover the background. Okay, so this is the Dantzig-Wolfe algorithm applied to the two-stage stochastic program. So if I ask you, is this any different from the L-shaped algorithm? Think of what you're solving here and ask yourself, if I do Dantzig-Wolfe on the dual, is it any different from just doing the L-shape on the primal? If you wrote this on code, what would it look like? So what is the algorithm saying? It says start from empty sets of rows and of extreme rays and extreme points. Solve this guy here in the first iteration. What are you going to pass to the sub-problem? You solve this, what do you keep from 3 to 5? The x's, the dual variables. You pass them to the sub-problems. Okay, even at this stage, have we done anything different from L-shape? We're basically solving the dual LPs of the L-shaped method. Other than that, it's doing exactly the same thing. So that's really just the difference. We're gonna solve a different LP, which is just a dual of the original LP. So we send the x's, then we solve the sub-problems. We check for variables that need to enter, and variables entering in the Dantzig-Wolfe algorithm corresponds to optimality cuts in the L-shaped algorithm. That's basically what's going on here. So in step 2, for all the scenarios, we look for candidate rays. If our sub-problem is unbounded, or if the objective function is less than theta, then we bring in, so if it's bigger than theta, sorry, we bring in extreme point. Okay, let's think of the bounds. How would you get a bound with these LPs here in your code if you were applying Dantzig-Wolfe? This master, is it an upper or a lower bound? The reason being, it is an upper, and again, the idea is that if this is our full polyhedron, what the Dantzig-Wolfe does is it says, okay, let's think what would happen if only these extreme points were considered. So let's basically optimize only over this space. This is obviously a constrained version of the true maximization problem. Sorry, it's a lower bound in that case. Sorry. It's going to be something worse than the true maximum. Okay, so that was a way to get lower bounds. Well, basically the dual of this problem, we just derived it over here. It's the same as solving this. And what did we say in the L-shaped algorithm? We were saying the solution of the master is underestimated through cost. Why? Because the value functions are underestimated by optimality cuts. So it's, again, even the derivation of the bounds is exactly the same idea. And the last thing to observe to complete this analogy is bounds in the other direction. If you recall, the way we computed upper bounds for Dantzig-Wolfe was we took the dual multipliers of the master, multiplied inner product with the right-hand side of the master, plus solution of the master problem. And we showed in the last lecture that this thing is an upper bound to the true optimization problem. Okay, and the claim is that this is the same as right. So the claim is that this is the same as the upper bound we get in the L-shaped method. Well, the upper bound we get in the L-shaped method is Z here corresponds to right, Z here corresponds to this guy. So indeed, if we have a feasible second stage Y vector and we add to that the C transpose X, given that X may not be the optimal one, we have an upper bound to our original optimization problem. So the bounds we're getting in both procedures are exactly the same. So these two things, Dantzig-Wolfe applied to the dual, or L-shaped applied to the primal, same thing. In terms of code, the only thing that's changing is you're solving dual LPs instead of primal LPs. That's really the only difference. Okay, but now, since we've learned this tool, this trick called Dantzig-Wolfe, let's see if we can use it to solve other types of problems. And the last bit of information I have for you in this class is how you can apply this specific tool to solve integer programs. Any questions with the application in two-stage stochastic programming? We are good. Okay. So let's think of how we can apply this algorithm to integer programming. This what you're seeing here is an integer program, basically integer linear program. You have C transpose X, where your feasible region is the intersection of two things, one polyhedron Y, one polyhedron Z, intersected with integer space. So the crucial assumption in what you're going to see in the next couple of slides is that this problem would have been easy if I didn't have this constraint set here. So if I was only minimizing C transpose H with respect to, sorry, if I didn't have the Y constraints. If I was just minimizing C transpose H, X with respect to X in capital Z, that would have been an easy problem. We can now exploit that idea, take advantage of it, to using Dantzig-Wolfe. We're going to break up this problem into pieces using Dantzig-Wolfe. So this is how we're going to do it. We're going to apply Minkowski. We're going to think of this polyhedron over here, which is the easy polyhedron, capital Z. And here there's a typo. This is Z intersect Z to the n. So this is a lattice. Basically, the way to think of capital Z is Z looks something like this set here. So again, it's the intersection of this thing, bx greater than or equal to b, intersected with the integer points. So capital Z is basically this lattice over here. What we're going to do is apply Minkowski to the convex hull of this polyhedron over here. Okay? And we're going to denote x superscript j as the extreme points of this polyhedron. Okay. So what we will what we would have gotten if we applied Minkowski to. So when I'm applying Minkowski, what I want to know is the set of all the extreme points of this polyhedron. And what I get is again the full master linear program if I consider all of them. But if I only consider a subset of the extreme points of this polyhedron, I get the restricted master linear program, which you have over here. So again, the tilde j is indicating that we're only considering a subset of the extreme points of this polyhedron over here. And you can use the same observations that we've done so far to derive the Dantzig-Wolfe decomposition algorithm on this optimization problem over here. Now, the one crucial thing to note is that the subproblems will be easy. So basically, we started by solving this problem by observing that if I did not have these constraints and I only had these guys over here, this problem would have been easy to solve. Now we're going to arrive to that as a subproblem in our decomposition. So basically, the Dantzig-Wolfe subproblems that we get are minimizing slightly modified coefficients of the original problem. So C is modified to C minus pi transpose D. But the important thing is the constraint set. So the constraint set in the subproblem is only the capital Z's. So we're left with just the easy constraints that we. So the takeaway here is if you're given an integer program, some parts of it, if you drop them, you get a familiar easy integer program that you have well-developed algorithms to solve. Then you can apply Dantzig-Wolfe and drop the constraints that make the problem difficult and just be left with the constraints that make it an easy integer program. One example is you could have something that's a bit more complicated than a knapsack problem. And if you throw away the extra constraints, you're just left with a knapsack problem. Knapsack problems are integer programs, but you can solve them rapidly. So you can apply Dantzig-Wolfe by writing capital Z as only those constraints that make this a knapsack problem. You're going to get a slightly modified objective function, but that doesn't make the problem much harder to solve. So that's the idea, basically. I don't want to torment you with too much more information. So this is basically the algorithm written out in detail, but if you understand Dantzig-Wolfe, you kind of get the idea here. And there's a couple of other slides that show that if you had taken the dual of this, the last piece of information in this presentation is that, again, we started with a problem where these constraints are difficult. How would you have solved this with Lagrange relaxation? What do you usually do with Lagrange relaxation to get bounds? If you know which the easy constraints are, how do you get rid of the difficult ones? Relaxant. So what would the dual function optimization? Okay, in this specific case here, what would the Lagrangian function look like? Which constraint would you like to relax? But you're told that you can solve this quickly. It's integer, but for example, if it were a knapsack, since it is a one deal. So which one do we want to throw away? Let me write this up. Here, I like the idea. How about the Lagrangian function? What about the sine of pi to get an appropriate bound? So actually this would be the dual function. We want the dual function to be a bound. Well, here's where you need to remember what is the whole philosophy. You want it to be an upper bound? Again, be careful. The relaxation. So you want a relaxation of this problem to be. This is a mnemonic. You know, when you're relaxing, you want your relaxation, if you're doing a minimization, to be a lower bound. Magically, you will arrive at a concave dual function that you can then optimize easily. So what should the sine of pi be? Negative. So in that case, I'm going to write this like that and make them non-negative. So I change the sign here for you. And this is a lower bound to our problem. Now, when you maximize this lower bound, this is what you get. This is the optimization you get over here. So what you can do is show that this guy is in fact equal to the solution of the Dantzig-Wolfe decomposition of the restricted master linear program. These two will turn out to be equal. The proof is in the last couple of slides. It's just a bunch of duality arguments, but I don't want to torment you with them and go over time. So it's kind of interesting, you know. You in Lagrange relaxation, you throw away constraints. In Dantzig-Wolfe, the idea is to approximate instead this polyhedron, but you arrive at the same bound. So, you want to apply Lagrange relaxation or Dantzig-Wolfe? Well, it depends which results in an easier decomposition. You get different subproblems with each of these approaches, but the bound you're going to get is going to be the same. So, you've seen how these techniques apply to stochastic programs, but you can go beyond that.